Great.
Welcome everyone to our last talk of the conference. So please introduce Lola Thompson from Utrecht University, who will be talking on pre-images of the sum of proper divisor function.
Thank you. So first I want to say thank you so much to the organizers for inviting me to speak. Even though I'm at Utrecht University, I'm American, in case you can't tell from my accent. And it's always so nice to be able to come back to my home country and see all my friends from the number theory community here. So I was really happy that I had this opportunity to come back. When I was after I was approached to give the talk, once I saw the schedule, but before I submitted my abstract, I had two potential talks in mind. And one of them involved arithmetic, hyperbolic, 3 orbifolds, and Mahler measure, and a lot of background material. And the other one was a more friendly talk involving the sum of proper divisors function. And when I saw that I was the last talk on the schedule, I thought, let's do the friendly one that involves the sum of proper divisors function. So I hope that this ends up being a nice, relaxing end to the conference. There's going to be a lot of pictures, a lot of history. So anyway, that's sort of my goal. So yeah, first off, in case you haven't encountered it before, we have the sum of proper divisors function, which we call S of n. And so it's just we take all the divisors of n and we exclude n itself, and then we add them together. And because every single thing in my talk involves using S of n, I'm going to put it on the board in case you space out and then later go, wait, what was S of n again? So I'll just write here, this is divisors of n, where d is less than n, and we're summing d. And I'm going to try to do this repeatedly because I know that at the end of a long conference, it's really hard to remember all the definitions. Okay, so some nice examples. We have S of p is always 1 because the only proper divisor of any prime is 1. And S of 12, well, we write down all the divisors of 12 except for 12, and then we add them together and get 16. So here's just some examples of this function. And when you see S of n, it probably makes you think of sigma of n, which is the more commonly used sum of divisors function. And fortunately, they're related. So we just can write S of n in terms of sigma of n minus n. One important distinction between these functions, so we like sigma because it's multiplicative and it has a lot of nice properties. S of n function is neither additive nor multiplicative, and that's what makes some of these results a little bit harder. And so that's one reason in particular why we study S of n, is because it's kind of not all figured out in the same way that a lot of things are known about the sigma function. Okay, so S of n, some people even consider this to be the first function that was ever studied. So there's a paper by Carl Pomerantz that's called The First Function and Its Iterates, and it deals with the S of n function. And that's because S of n goes all the way back to Pythagoras in the ancient Greek times. And so Pythagoras noticed that if you take 6 and you add its divisors, its proper divisors, then you get back 6. And he liked this property so much, he called 6 a perfect number. And he discovered other examples of perfect numbers like 28. So in particular, he defined numbers to be perfect if you plug them into the S function and you get them back. And the perfect numbers, again, because they're so old, there's a lot of history behind them. And I was digging around online to find some quotes about perfect numbers. And I really liked this one by Augustine, who kind of gets religious about it. So he says, 6 is a perfect number, is a number perfect in itself, and not because God created all things in 6 days. Rather, the converse is true. God created all things in 6 days because the number is perfect. So we can explain all of religion through number theory, apparently. So anyway, I kind of like that, as a number theorist. So Pythagoras also observed that there's this nice property when you plug 220 into S. And so in particular, S of 220 gives you 284. And then if you plug 284 into S, you get back 220. And so, he liked this property, and people now refer to this as an amicable pair. So as of yesterday, when I was finishing writing these slides, I looked online. You can find like a current tabulation of all the amicable pairs that have been found, and it's over 1 billion at this point. So anyway, there's a huge number of amicable pairs that we know about. And once again, you can find some really funny quotes about amicable pairs. So Pythagoras himself, when describing friendship, he said, "One who is the other I, such as 220 and 284. Very sweet. Interestingly, I learned recently that around 1,000 years ago, the sort of, Islamic mathematicians we're also looking at the S function, and in particular at the inverse of S function. And they had various things to say about it. But I thought this quote was very strange. So Al-Majridi said around 10th century, the Common Era, that I have tested the erotic effect of giving anyone of the smaller number 220 to eat, and I myself eating the larger number 284. So first off, I have no idea what could possibly be erotic about this. But secondly, what does it mean to eat a number? So anyway, I don't know what this quote means, but I thought it was really interesting, and I was able to even find a picture of him on a stamp from Spain. So anyway, that's Al-Majridi for you. We have also modern examples involving amicable numbers, thanks to XKCD. So there's this comic that says, this professor standing at a board giving a lecture like I am right now, saying, in my paper, I use an extension of the divisor function over the Gaussian integers to generalize the so-called friendly numbers into the complex plane. And then one of the audience members, like you all, says, wait a second, is this paper simply a giant buildup to an imaginary friend's pun? And yeah, I guess the answer is probably yes, if you can read the last panel there. So as you can see, they enter popular culture quite a lot. Here's my last pop culture example. You can go online to MRCR Unique Creations and actually several other websites, and you can find examples of friendship necklaces and friendship keychains that involve the numbers 220 and 284. So it's kind of sweet. All right, so we like perfect numbers. We like amicable pairs. But now there's this question, well, what about other numbers that we apply S to? And you can actually kind of view S like it's an amicable system and apply S repeatedly and sort of see what happens. And so as we saw earlier in my talk, we know that S of 6 is 6, S of 28, as I said, is 28, and we have the amicable pairs here. But if you apply S to 8, for example, then you get 7, and then you apply S again, and because 7 is prime, it has only one proper divisor, 1, and so then the chain ends. And so you see, we either kind of get these cycles, or we get these chains that go down to 1, or we get 276, which we don't even know what the heck happens with that. So with numbers like 276, over 2,000 iterates have been checked for plugging it into the S function. So you just, you get 276, you plug it into S, you get 396, you just keep going and going over 2,000 times. This chain has not ended. And this has been checked up to like, I think 210 digit numbers or something crazy like this. So anyway, there's all kinds of things that can happen when you iterate S, and we call these sequences of iterates aliquot sequences. And there's some interesting conjectures about aliquot sequences. So Catalan and Dixon conjectured that every aliquot sequence is bounded. And then Guy and Selfridge gave a counter conjecture saying that most aliquot sequences starting from an even number are unbounded. So we don't know a single example of a sequence that is definitely unbounded, but like I said, 276 seems like a pretty good candidate at this point. There is some evidence against both conjectures, though. So evidence against Catalan-Dixon is that there have been these computations by Bosma, who started with all these numbers below 10 to the 6, and he looked at their aliquot sequences, and he was able to observe that approximately a third of the ones that have even starting numbers yield aliquot sequences that haven't terminated yet. And he's computed this up to 10 to the 99. On the other hand, for Guy and Selfridge's conjecture, so Bosma and Kane found that if you take the asymptotic geometric mean of these ratios of even numbers, S of even numbers over themselves, this asymptotic geometric mean is slightly below 1. So then this idea that the even number starting ones are unbounded maybe doesn't seem quite as plausible if that's what the asymptotic geometric mean is. So to answer any questions you might have, we have no idea if these conjectures are true or which one is more likely to be true. But that's kind of the state of affair with this question about these aliquot sequences, at least. And one more chance to try to plug for you that these numbers are interesting, and I'm not just telling you fun recreational stuff at the end of a long conference. So Karl Pomerantz has this great quote that I stole, and he said, studying the comparison of S of n to n led to theorems of Schoenberg, Davenport, and Erdős-Wintner, and to the birth of probabilistic number theory. And it's true that a lot of ideas from probabilistic number theory were developed in order to study this relationship between S of n and n. So anyway, it's an interesting thing to study because it gives birth to other interesting things. In this talk, we're going to focus on two types of questions. Oh, is that a question, Angie? Yes. So, right. So aliquot sequence is just when you take the iterates of the S function. And yeah, the ones that are interesting to study are the ones that don't just like go into a cycle, of course. But yeah, so these are all examples of aliquot sequences. Okay. So yeah, so we're going to focus on two questions in this talk. One is what happens when so we're going to view S as a function. And then with functions, you can always look at their image and their pre-image, right? So we're going to look at the image of S and say what lives in the image of S. And then we're going to take specific sets and apply S inverse to them and say, what does S inverse do to these sets? So those are going to be the two main questions. And then at the very end of my talk, I'm going to introduce integers with missing digits and say a little bit about something we can do that involves those. So that's kind of giving you a rough outline of what I'm going to do. Most of the talk is really going to focus on this second question here. And actually, that's a good moment to say, are there any other questions before I really dive into the content of the talk? There's any bound on S of n? You mean in terms of how large it can get? Yeah. No, it just can keep getting larger. Question. The p-adic norm of. Oh. Right. That's interesting. I honestly don't know. It's a good question. Can look and see if you can find the answer, and if not, we can try to figure it out or talk about it more later. But yeah, I have no idea. Any other questions? Yes. Oh, that's what you mean. Sorry. Like, yeah. So there are bounds in terms of n. Right. No, I just was thinking in terms of like, if we follow these sequences, can we keep going out further? And the answer is yes. But yeah, as a function of n, there are bounds. So you're right. So we can bound S of n in terms of n to the 1 plus epsilon. But yeah, the numbers themselves can just keep getting bigger and bigger, as we've seen with these aliquot sequences that don't seem to terminate. Like, can every time you think you find a big number that is, it's after a bunch of iterates of S, you can sometimes find a bigger number. So yeah. Okay. So any other questions? Okay. So yeah, so Erdős was the first to really kind of consider the image of S questions. Of course, now I've been finding out that 1,000 years ago, the sort of Moorish mathematicians were also thinking about S of n, and so maybe there's a bit of history there that I don't know about. But the first papers you can really find about the image of S are due to Erdős. So I'm going to sort of give him credit for this line of thinking. So the first fact that I want to tell you about with the image of S is that it turns out that almost all odd numbers are actually contained in the image of S. And in order to show this, we're going to appeal to a variant of the Goldbach conjecture that is actually known. But before I dive into that, let me just review for you what we do know about the Goldbach. So we know that, the ternary Goldbach conjecture is true and has been proven. And we still don't know about the sort of one we all think of as the Goldbach conjecture, which says that every even number greater than 2 is a sum of 2 primes. And then this XKCD comic proposes some pretty preposterous, very weak and very strong forms of the Goldbach conjecture, which are obviously not, they're either not true or they're like very obviously true, right? I really like this one. There are no numbers above 7. It's a very strong Goldbach conjecture. Or the extremely weak one. Numbers just keep going. Anyway, so yeah, I like to share this slide just because it's sort of a fun thing in the middle of the talk. Okay, so let's think about why almost all odd numbers would be contained in the image of S. And this kind of comes down to just studying one particular family of numbers. So what we can do is we can take pairs of distinct primes and we can apply S to them. You take the product. And then, of course, the only proper divisors you get are just 1 and then each of those primes themselves. So you add them together, and that's S of PQ. And then by this strong Goldbach conjecture, it says that all the even numbers that are at least 8 can be written as a sum of 2 unequal primes. And this is actually known for almost all even integers except for a set with asymptotic density 0. So we don't actually need the Goldbach conjecture to be true. We just need this kind of almost all statement to be true, which we do know is true. But then, of course, when you just add 1 to even numbers, you get odd numbers. And so that tells us that almost all odd numbers, at least 9, are going to be values of S. And so this gives us a very nice, simple family to look at in order to see this result. Okay, so we know about odd numbers in the image of S. Now, what about even numbers in the image of S? So Erdős showed in 1973 that a positive proportion of even integers are missing from the image of S. But then Florian Lucke and Karl Pomerantz in 2014 showed that a positive proportion of even integers are in the image of S. So you have a positive proportion kind of in both of the two options. Okay, so we know a bit about even versus odd numbers and where they live in terms of the image of S. The S function is weird. I mean, I mentioned before, it's neither additive or multiplicative, but also it can take sets with asymptotic density 0 and map them to sets with positive asymptotic density, which I guess initially I found a bit surprising when I learned this fact. And so we actually just saw this in the example that I mentioned. So we have this product of p times q primes. If you want to compute the asymptotic density of that set, it's 0. And you can just see this if you actually want to count the elements in the set A. It's bounded above by big O. It's like big O of x log x over log of x. And so then if you compute the asymptotic density, you just take 1 over x times the thing, and you take the limit as x goes to infinity. And so you get something like log x over log x as x is going to infinity. So this is going to 0. So that's how you see that A has asymptotic density 0. On the other hand, we saw that the odd numbers were all in the image of S. So this is how we're getting a set with positive asymptotic density in the image, even though we started with a set of asymptotic density 0 to begin with. Erdős did something even weirder. And so he constructed sets A that have positive density, but where you apply S inverse to those sets, and in fact, they don't just have density 0, they're actually empty. So that's another just weird example of how S behaves. Like, I think it's really interesting that you know, S can take these extremely sparse sets and like map them to a whole lot of things. Question? Yes. So if you actually count it, which I didn't argue how to count it, but if you go through the effort of trying to count the elements in this set, it turns out that it has size x log x over log x if you're counting products of p times q going up to x. And that takes a little bit of work to show. It's not too hard. But once you have an x log x over log x, then you take the limit as x goes to infinity, and you take 1 over x, and then that gives you log over log, which is tending to 0. Yeah, so that's the idea. Okay, so that's all I really want to say about the image of S, because like I said, the main goal of this talk is pre-images under S inverse. And let me actually double check how I'm doing with timing. I'm fine. Okay, so there's this question, what can we say about S inverse of a set if that set has asymptotic density 0? That's our motivating question in this talk. And it's our motivating question because we have a conjecture due to Erdős, Granville, Pomerantz, and Spiro, which says that if you have a set with asymptotic density 0 and you apply S inverse to that set, then it should also have asymptotic density 0. And this is still not proven, going all the way back to 1990. But it has been proven in certain special cases for the set A. And so I'll tell you a little bit about what's known and sort of the limit of our understanding. So Paul Pollock in 2014 showed that if A is a set of primes, well, A has density 0. And then if you apply S inverse, this also has density 0. And then his PhD student, Lee Troop, showed that if your set A is a set of integers with a lot more than the normal number of distinct prime factors, then S inverse of this set also has density 0. So here, in order to understand why this implies the EGPS conjecture is true in this case, you have to realize that numbers that have a lot more than the normal number of prime factors are also very rare. And so The set A itself has asymptotic density 0, and then we apply S inverse, and that has asymptotic density 0. Paul Pollack also studied palindromes, which are also a density 0 set, and showed that if you apply S inverse, still has density 0. And then Lee Troop in 2020 showed that if you look at sets of integers, that can be written as a sum of two squares. Well, again, that's a set of asymptotic density 0, and if you apply S inverse, it has asymptotic density 0. So these are all examples of sets that obey the EGPS conjecture. But the kind of crucial element in all of these proofs is really having to do with the structure of these sets A. So the proof for this one, for Pollack, really relies on the fact that you're looking at palindromes. It's not something that applies to other sets. It's like very palindrome specific. And same thing for these other arguments. They all really rely on the structure of the set of integers that you're studying. So I'm going to come back to this issue in a minute, because obviously if you want to try to prove the EGPS conjecture, you don't want to limit it. You don't want to have like a proof for every type of number, right? And so the ideas used here don't really generalize in a nice way, unfortunately. I just wanted to mention a few more recent results and give a bit of a shout out to some of Paul's other PhD students. So Paul and Akash Singh Roy in 2022 showed that if you have any fixed k that's at least 4, then the kth power free values of n and the kth power free values of S of n are equally common. And then Paul, along with Akash and Noah Lebowitz-Lockard, showed in 2023 that the values of S of n when n's composite are equidistributed among the residue classes mod p, and this is true for small primes p. And then finally, I like this one by Paul Pollack and Lee Troop from 2023. They proved what's called an Erdős-Katz type result. So they showed that the function little omega of S of n, so this is the number of distinct prime factors of S of n, has the same mean and variance as omega of n. And so omega of n, we know, has mean and variance log n. And so they showed that even when you take omega of S of n, it still has mean and variance log n. So anyway, these are just some results again about the S function. And here's pictures of all the people that I mentioned. So Paul and 3 of his PhD students. So what I would like to now mention is a result of mine from 2017 with Paul Pollack and Carl Pomerantz. And what we wanted to do is get away from these restrictions on the structure of the set A. So we didn't want to have results that were specific to palindromes or sums of two squares or primes or whatever. We just wanted to say, if you have a set of a certain size, who cares what's in that set? Does that set obey the EGPS conjecture? And so we were able to get this for sets of size up to x to the 1/2 plus epsilon, where epsilon here is a function tending to 0 with x. So epsilon's actually a function of x here. And so as long as your set has size at most x to the 1/2 plus epsilon, where epsilon tends to 0, then you do get that these sets, which have asymptotic density 0, when you apply S inverse to them, also have asymptotic density 0. You can see that the size of these sets is little o of x, where that little o depends on the epsilon that you chose. And so I'm going to say a little bit now about how we do this, and then actually this result will come up in the second part of my talk when I get into the integers with missing digits as well. But first, let me tell you some consequences of our theorem. So in particular, we get a reproof of Paul Pollack's result on palindromes, because the set of palindromes has size smaller than or equal to x to the 1/2 plus epsilon. And we get a result that if you look at the set of squares, which has size big O of x to the 1/2 plus epsilon, or big O of x to the 1/2 really, then you get S inverse of that set also has asymptotic density 0. So we get some results for free just by using this result about sizes of sets. And that's going to come up, like I said, later in the talk when we talk about integers with missing digits as well. All right, so let's see how I'm doing. Yeah, I think I'm still okay. So I think we do have time to talk a little bit about the proof. I'm just going to give a sketch. So first off, we can just assume that our epsilon is at least 1 over log x. But again, remembering that our epsilon has to tend to 0 with x. So it's a function that still tends to 0 with x, but we can bound it below by this. It just makes the stuff easier. Okay, and then we're going to let A be a set with the size that we said. And when we're counting our m's up to x, where S of m is in our A, And I think that should have been, oh, I see, yeah, because M is so it's a little bit confusing. M is the image of S of N. So like you're thinking of counting M's up to X so that S of N is equal to M and M is the most X. I read that a little funny. Anyway, so when we're counting M's up to X where S of N is in A, we're going to throw out all the N's that are inconvenient for our purposes. And so I list a whole bunch of criteria here. And the good news is that by assuming all these facts, it just makes our proof easier. But it doesn't matter that we assume these facts because the N's with these properties all have size little o of X. And so it's okay. If we throw them out, it doesn't affect our overarching estimate in the end because we're just trying for a little o of X type result. We're not being super precise. And so in particular, we're going to throw out everything that is smaller than X to the 1/2. We're going to throw out everything that has no prime factor up to log X, where the square full part is big, where the GCD of N and sigma is big. And this one is really key, where N has a divisor that's between X to the 1/2 minus 10 epsilon and X to the 1/2 plus 10 epsilon. So, I mean, I realize this last condition sounds a little bit weird, but just for some reason, when having a divisor in here, we're going to really crucially use the fact that our numbers don't have any divisors in this range, which you'll see in a minute. So we're throwing out all these things that just make our proof not work, and that's okay, because the things that we're throwing out live in small sets. Okay, so then our proof strategy is we're going to show that for every A in our set A, the number of remaining N's up to X, where S of N is equal to A is going to be at most X to the 1/2 minus epsilon. And so this is really a pointwise bound because at different points A, we are explicitly showing that S of N doesn't have, the number of these N's doesn't get too big. So we're doing first a pointwise bound, and then because we have our size of our set A being at most X to the 1/2 plus epsilon, then this pointwise bound turns out to be enough to give us the little o of X result that we wanted. And so really the crucial piece of our argument is this sort of pointwise bound. And this pointwise bound actually came from adapting an algorithm of Andy Booker. So Andy Booker wanted to compute S inverse of points and determine, in an efficient way how to find S inverse of these points. And he was doing this actually to study iterates of the S inverse function. So he wanted to look at S inverse of S inverse, kind of like we were doing with aliquot sequences, but kind of inverse aliquot sequences. So that's where that came from. But we're able to basically adapt this idea of Andy Booker to get the pointwise bound, and then we're able to get the rest of the result. Question? I can't remember the actual shape, to be honest. I'd have to go back and look at the paper. This one's from 2017, and so I don't remember the exact shape that we got in the end. But I can take a look after, or you can look up the paper online right now and then tell me at the end. But yeah, I don't remember what our exact little o is. All I care right now for this talk purpose is that it's a little o. Yeah, I tried to sweep a lot of like the ugly analytic number theory under the rug for the talk. So anyway. All right, so the question is, where does this pointwise bound come from? And so what we do is we factor N into D times E, where D is the largest divisor of N not exceeding the square root of X. And we are going to bound the number of possibilities for this E given our choice of D, and then we're going to sum over all the possible Ds. So that's the sort of strategy. And then remember that 2 slides ago, I made this long list of assumptions about my N's. And one of the assumptions is that it didn't have any divisors between X to the 1/2 minus 10 epsilon and X to the 1/2 plus 10 epsilon. So in particular, this means we can pick things so that our D is less than this, but then when we multiply it by the next prime divisor of N, then we get something that is bigger than X to the 1/2 plus 10 epsilon. And that's how we don't have any divisors inside that range. Okay. And then from these inequalities, we can actually deduce, because of the fact that N has a small square full part, that D and E are actually relatively prime. And so then we look at S applied to product D times E, and we're, solving this equation, S of D times E equals A. And we just use the multiplicativity of sigma and the definition of S in terms of N minus sigma, or sigma minus N. And we can factor things in this way. So we have a sigma of D times S of E plus an S of D times E equaling A. And so then in the end, it's enough to bound the number of possible choices for S of E, given our choice of D. And then since D and S of E determine our E, then they determine the ends that are equal to D times E. And this equation also tells us, if we view it instead as a congruence mod S of D, that we have sigma of D times S of E is congruent to A mod S of D. And so then, given our choice of D, this means our S of E is in a uniquely determined residue class mod S of D divided by that GCD. So okay, we now have something that is easier to work with in terms of counting. So just to remind us of where we're at, given D, we want to count the number of possibilities for S of E. And we know that S of E is in a uniquely determined residue class mod this fraction from the previous slide. And so now we want an upper bound on S of E. And it turns out a lower bound is easy. So you can just lower bound it by taking E over the smallest prime factor of E. The lower bound itself isn't actually helpful, but it turns out that the lower bound is not actually too far from the truth. So you can bound S of E above, and this is the part I'm sweeping under the rug a bit, but with a little bit of work, you can bound S of E above by big O of log of X times E over the smallest prime factor of E. And so I'm recopying that from the previous slide there. And then what we do is we use the fact that since D times E is N and our N's are going up to X, then of course our E is going to be at most X over D. And so then we can just replace this expression with this expression. And then we remember that we had this bound on D times the smallest prime factor of E from a couple of slides ago. And so again, we can put that into here and we get this instead. So I'm just substituting in all these assumptions that we made on the previous slides. And then sort of as a little recap, so my S of E is now in a uniquely determined residue class modulo this fraction. And I also have this bound on S of E from the previous slide. And then this tells me that the number of possibilities for S of E, given our choice of D, is then going to be something like this. I added a 1 as a little fudge factor just to kind of, in case anything is a little bit off. And then what we end up doing is we use the fact that we can lower bound S of D, just like we did with S of E, by D over the smallest prime factor of D. And then we get that this is at least D over log of X. And also there's this nice thing about GCDs. So if we take the GCD of S of D and sigma of D, it's the same thing as the GCD of D and sigma of D. And that again comes from that equality we have with the S of D being sigma of D minus D. And then this, of course, divides the GCD of N and sigma of N because our D divides N. And therefore, this tells us that our GCD here is at most the logarithm of X. So in conclusion, putting all this together, we get an upper bound that takes this log of X and the log of X that we were dividing by in the denominator. And so we bring those both upstairs, and now we have a log cubed of X because we already had a log of X, and then everything else comes from the rest of this expression. So that's how we get an upper bound. This is how we get our pointwise upper bound. And then, like I said, we put our pointwise upper bound in. And then if we go back to here, we then kind of finish the second step of the proof, which I'm not going to have time for in this talk, which is okay. But I kind of showed you a sketch of how we do the first step, at least. So this gives you a rough idea of how these kinds of arguments work. And actually, this is not unique to our proof with Paul and Carl. All of the arguments that deal with sets A that have specific structure, like palindromes, like primes, et cetera, they all start by kind of taking a bunch of conditions for things they're throwing away. So they all start with saying, let's look at ends where, the prime factors are, the smallest prime factors are not too big, and where we need there to be a divisor in a certain range, that kind of thing. So there's always kind of this list of conditions, and then the list of conditions always ends up helping with getting the right kind of bound that you want. But of course, with the ones that have a specific structure, then you have to incorporate like what we know about palindromes that makes them special. So that's kind of the difference between what we do, where we don't have to like incorporate anything about A, except for its size, versus other people where they really need to use things about the specific set A. So anyway, that's just like a little flavor for the kind of argument I did with Carl and Paul. I want to mention that that bound hasn't been beaten yet. So the best known result still for trying to compute or trying to show the EGPS conjecture for sets of a certain size is this x to the 1/2 plus epsilon. So I would love it if someone could get higher than x to the 1/2 plus epsilon, but that hasn't been beaten since 2017. So anyway, that's a thing for people to think about. So what I want to now do in the last bit of time that I have, and I think I have like 15 minutes, is that right? 15 to 20, okay. So what I want to do in the last bit of time that I have is I want to talk to you now about, we're still going to think about the EGPS conjecture, but now we are going to apply it to a specific set A. And the set A, they're going to be sets of integers with missing digits. And so kind of now we're going to change gears. And instead of worrying about sets of a certain size, we're going to worry about sets of specific structures again. And so I'm switching gears to integers with missing digits, and I have this really sad looking 7. And the reason the 7 is sad will become apparent in a couple of slides. But first, some notation. And again, because this is the end of the conference, I wanted to put all my notation on the board because I'm about to have a whole bunch of statements in terms of these WDs and WD of X's, and it's very easy to forget what they mean as soon as I click to the next slide. So I'm literally going to copy this onto the board. So we are going to let W sub D just be the set of integers n that live inside of the natural numbers. And this is going to be where we write things in the form n is equal to the sum of epsilon sub j's times g to the j. And we are going to sum over j's that are at least 0. And we are going to make our epsilon sub j's come from the set D. And so what this is doing is this is saying, and maybe I'll even mention here that my D is a subset of the number, as a proper subset of the numbers 0 up to g minus 1. And so what this is saying is that we're excluding at least one digit, right? Because we're taking a proper subset. So we're saying exclude at least one digit. And then we're looking at sets of integers that have coefficients coming from this set of possible digits with at least one excluded. And then this is just the base raised to the different powers. So we're writing it in, binary or decimal or whatever, depending on what our G ends up being. And then the other thing that we need is we need a counting function because we're going to count things because this is an analytic number theory talk. And so we have what we call WD of X. And WD of X is just defined to be, well, what happens when we take WD and we intersect it with the interval from 1 up to X. And so that's how we're going to count elements in WD, is by looking at WD of X. And it's important to note that this set has asymptotic density 0. Okay. So that's my notation. And like I said, I'm going to use this WD and WD of X from now on. And it's super easy to forget. So I put it up here just in case. Okay. So there's a lot of results on integers with missing digits. Erdős, Mauduit, and Sarkozy showed in 1998 that integers with missing digits are well distributed in arithmetic progressions. And there's a lot of very hard work with very specific bounds by what we mean by well distributed. I'm not going to get into that in this talk. But you can look at papers by Konyagan, Cole, et cetera, in order to find out precisely what this means. If you want something more quantitative in terms of what we mean by well distributed. But there's also this result by Cécile Dartige and Christian Mauduit from 2000. And this says, and by the way, the French people often call these ellipsephic numbers instead of integers with missing digits. So you might see this word ellipsephic floating around. But anyway, they show that there's infinitely many n in the set with, well, we just have like very prescribed digits here, 0 and 1, but that have at most this number of prime factors as g tends to infinity. And so you can summarize this result by saying they're looking at almost primes, so numbers without too many prime factors. And they show that there are infinitely many almost primes with restricted digits. So that's their result. But again, there's tons of work by people like Cécile Dartige, Christian Mauduit, et cetera, having to do with this. I'm just giving a very brief overview for the sake of this talk. So the one that everyone's probably familiar with because it was in the news and it got James a Fields Medal partly, I mean this and a lot of other things, is James Maynard asked, are there infinitely many primes that have a given digit missing? And the one he liked to exclude in all of his talks, and he mentioned specifically in his paper, is leaving out 7. And that's why I had that sad 7 a few slides ago, because 7 is being excluded. So one thing to notice is that if we sum the reciprocals of primes, we get, it's infinite if you take the sum, right? It diverges, the series diverges. And this is one of the ways that we teach our students how to show that there are infinitely many primes, is by showing that the sum of reciprocals of primes diverges. On the other hand, if we take the set of primes that don't have any 7s in their decimal expansion, and we take 1 over those and add them, we get something that's bounded by 100. So what this tells us is this set of primes is a very thin set compared to the full set of primes. And the thing about thin sets is they're harder to handle using things like sieve methods. And so what has to happen then is James had to figure out how to overcome this extra challenge of applying sieving techniques to extremely thin sets. And that was really, I think when you describe the problem about, proving there's infinitely many primes with missing 7s, like it maybe sounds again a bit like recreational or fun, but then when you dig into like the actual sieve stuff that he's doing, he's really showing very robust results about extremely thin sets with sieve methods. And I think that's like the power of this particular work of his. Why 7? He liked excluding 7. So certain other numbers have like very obvious sort of divisibility criteria, right? Like if you want to exclude like 3 or something, right? Like you can kind of easily check divisibility by 3, but maybe divisibility by 7, it's like a little less obvious. So it kind of feels like sufficiently random thing to exclude that, I don't know. Or like if you have like 2, like for example, there's this last digit phenomenon. Like if you look at the last digit in a number, of course, it can't be prime if it's divisible by, if it has a 2 in it or a 5 in it or certain things. And so I think he wanted to pick something that doesn't have this last digit phenomenon. That would be my guess. So I think he picked 7 just because it's kind of like it feels more random than some of the other ones, and in that sense, it's not going to like fall prey to some like obvious thing that anyway. Okay, so yeah, his famous result, as I alluded to, is he showed there's infinitely many primes with missing digits, so you can exclude 7 or you can exclude any other number, and it still works out. Now, I do not want to get into his proof techniques at all in this short remaining time that I have. But what I will show you is my PhD student, Sebastián Carrillo Santana, was studying this paper, and he made this like schematic diagram, which I know that nobody can read except for me, and I can even barely read it. But the point of this is it shows kind of all the pieces of the argument of James and how they come together. So you have so down here, you have the large sieve, which he used for type 1 estimates. And if you don't know what type 1 estimate is, that's fine. And down here, you have the geometry of numbers. And over here, you have the circle method. And up here, you have Harman sieve, which is a very powerful modern sieve. And there's also Markov chains floating around somewhere. And so you can see like all the different types of math that come together in order to overcome this obstruction of having really thin sets that don't play nicely with normal sieve methods. And so that's really like, I put this slide up here not because I expect you to read any details, but just to show like how incredibly complicated this paper of James's is and just how much work went into proving this. Okay, so James also has results for polynomials. So you can look at polynomial values with missing digits. And so in particular, he shows there's infinitely many integers n, so that when we plug them into polynomials, and again, these values have to live in our set of prescribed digits, so excluding things that aren't allowed. Then for any given non-constant polynomial in z adjoin x, where the base g is large enough, and again, you have to be excluding one possibility from your set. And I see James shaking his head. There's a separate issue that we'll talk about, him and I. But anyway, there's like maybe some things in this paper that are or are not completely correct according to James. But anyway, the stuff that we do, fortunately, doesn't rely too much on this. So I think our result is still okay. At any rate, so this is a paper of James that doesn't require quite as much of the really hard stuff as what needed to be done in his original paper. Okay, So that's the result that we're gonna use some of the methods from this in order to do our stuff. So now what I want to do is tell you specifically what my collaborators and I did. So this was a Women in Numbers Europe project. And so many of you know about Women in Numbers. Well, when it happens in Europe, it becomes wine. And there is a lot of wine. So this is my group here. This is Kubra Benley, Cecile Dartige, Julia Cezana, and Charlotte Dombrowski. And so the 5 of us met together in the beautiful city of Utrecht, where I live, and we worked on this project as part of Women in Numbers Europe 4. And so we specifically studied what happens when you apply S inverse to these sets of integers with missing digits. And maybe just, again, for the sake of following, I will put the notation on the board so that when I get to the slide where I use it, it's not completely confusing. So we're just going to take W sub S comma D to mean what happens when you apply S inverse to W of D. Okay, so let's talk a bit about what we did. So the first thing we did on the very first day that we met is we said, okay, let's let A be a set of integers with missing digits in any base that's at least 3. And I'll mention in a second why we need that restriction that's greater than or equal to 3. Then we can show that S inverse of A has asymptotic density 0. And so in particular, this means that the EGPS conjecture holds because sets of integers with missing digits have asymptotic density 0. And when you apply S inverse, we showed this still has asymptotic density 0. So the reason we exclude 3 is because in our proof, we have a lot of little logarithm of g's floating around. And it turns out log of 2 is smaller than 1. And because of the fact that E is, between 2 and 3. And so anyway, this is why a lot of what we do doesn't exactly work when G is equal to 2. So some of the things that we bound end up falling apart a little bit because of the fact that log of 2 is smaller than 1. All right, so anyway, what we really do, so here, this was kind of the simplified version of what we do, but if you want to get more quantitative, we actually can count the number of integers where S of n has all of its digits in base G restricted to a set D. And our count is actually big O of x over an exponential function. So it's big O of x over e to the log of x raised to a gamma, where gamma is allowed to be anything between 0 and 1, not including the endpoints. So this is really the quantitative version of our result, but I wanted to first give you the friendly version just to make it clear that EGPS is the thing that we're showing. The EGPS conjecture holds for these integers with missing digits. And so maybe I'll say a few words about sort of how good this upper bound is, because that's always what you should ask when you see an upper bound is like, is this any good? Is it sharp? So remember from the very first slide of my talk that S of a prime P is always 1. That's the only proper divisor of a prime. And so if our set D contains the number 1, then what this means is there are at least as many things in this set of integers that have prescribed digits as there are prime numbers. Because every prime is going to be something that produces a 1 when you apply S to it. And so in particular, this set is bigger than or equal to pi of x. And we know from the prime number theorem that pi of x is asymptotically x over log of x. And notice that if we kind of ignore this gamma here, and if we just took e to the log of x, well, that's like x over log of x. And so you can see that this is sort of the best we could really hope for. We can't replace gamma with any constant that's strictly larger than 1. And so anyway, in that sense, our result is sort of optimal because, yeah, we can't make our gamma any bigger and still have something that's true. All right, so now what I want to also mention is we get a nice corollary of my work with Carl Pomerantz and Paul Pollock. So remember, this was the statement that I had back earlier in my talk, where we said if you have sets of size at most x to the 1/2 plus epsilon, then the EGPS conjecture still holds on those sets. So in particular, if you want to remove a lot of digits from consideration, so if you want to restrict your set to integers where at least half of the possible digits are excluded, then the size of this set of integers with missing digits is big O of x to the 1/2, and 1/2 is smaller than 1/2 plus epsilon. And so then our result with Paul and Carl applies, and it shows that the EGPS conjecture holds for this set. So when you throw out a whole bunch of digits and you really restrict yourself to only half of the possible digits or less, you get this for free from my work with Carl and Paul. And then I want to end by mentioning an application of James Maynard's work. So if we look at this function S of n, we can show that it takes infinitely many values in the set of integers W sub d, where again, you have these prescribed digits and you're excluding at least one of them. And this comes back to the very first example that I gave when I started talking about things like looking at the image of S and getting almost all odd integers in it. So we can take S of P times Q, which again, from earlier in the talk was P plus Q plus 1. And earlier on, yeah, we use this to say almost all odd integers are in the image of S. So we already know that about this set. And so if we want things in the image of S that take on values in W sub D, well, we've already satisfied one of those two criteria. Now we have to think about showing that a positive proportion of integers that have missing digits can actually be written in this form. So you want to show that a positive proportion can be written as 1 plus a sum of 2 primes. And then in order to show that a positive proportion of integers with missing digits has this property, that's where we go into the methods of James's polynomials paper. And so in particular, we follow chapters 6 to 8 of his paper. And this requires using the circle method and sieve methods, but we don't have to slog too much through the stuff that he does. And in the end, we end up confirming that yes, a positive proportion of integers with missing digits can be written in this form. And so as a result, we have things that lie in the image of S and that have missing digits. And so we do then get infinitely many values of S of n in W sub d. So just to summarize, because I know it's the end again of a long day, a long conference, what we have shown in this talk is that surprisingly little is known about the function S of n. And as a reminder, Erdős, Granville, Pomerantz, and Spiro showed that if you take S inverse and apply it to set of or they conjectured that if you take S inverse and apply it to sets with asymptotic density 0, you get sets with asymptotic density 0. And in my talk, I've now told you about ways of doing this for specific sets with specific structures, and also for sets of certain sizes up to big O of x to the 1/2 plus epsilon. But the EGPS conjecture is still open, and places where you could make more progress on it are either by trying to get this bound to go higher, or by considering other types of sets with specific structures. And so those are two possible avenues for further investigation. But I will go ahead and end my talk there. So thank you all for listening.
Thank you. Are there any questions for our speaker?
Got lots of questions during the talk too, so I don't have to. We don't, like if you have questions, I'm very happy to answer them. But also, if there's no questions, I won't feel insulted.
So so you're bound on restricted digits. You said was optimal in a sense. With if you exclude 1. Is it still optimal in this similar sense?
No, so probably not. I mean, the 1 is really what sort of forces that, and then yeah, we didn't actually try to exclude 1 and prove a different version without 1. But yeah, it was immediately very clear to see that the 1 sort of this was the best you could do if you include 1, and then we didn't really try to create sets that don't include 1. It's actually very common in this integers with missing digit stuff to either include or exclude 0. So that's kind of the digit that people like to either like very forcibly say this should be considered, or very forcibly say no, 0 is like a weird exception. But yeah, one is kind of like always a possibility in all the literature. So we didn't try excluding 1.
Okay. Are there any other questions? Let's thank Lola again.
Thank you.